quizzes in a second. He's going to fetch them for me out of my mailbox. But for starters, do you have any questions about the homework or anything right now? Did I get it? Y'all saw it, didn't you? It did post. Isn't that right? Okay. Y'all, did you have any questions at all? I'm going to go through a few things that are real important today. I'm going to start by just showing you how to get the trigonometric Fourier series out of the exponential. And then I'm going to go through a method that you'll thank me for in the classes you have later. It's a very clever way of getting that value C of n without doing integrations. So before I say anything more, we know that if you have any periodic signal at all, doesn't matter what it is, it can be anything at all, like this in time. And this is time, the period is t, and we know that f naught, the fundamental, is 1 over t, and omega naught is 2 pi over t. Both of these are fundamental frequencies. One is in hertz, the other is in radians. Then the next thing, if this is x of t, and it is periodic, I know I can represent it as the exponential Fourier series, where n goes from minus infinity to infinity of some value C of n times e to the j n omega naught t. That's a doubly infinite exponential series. It goes from minus to plus infinity. Is that the quizzes?
Yes, sir.
Just start passing them back right here. Now the value of C of n we can get by doing an integration, technically. The integral from any value, I like to go from minus t over 2 to any value plus t. So if you start at minus t over 2 and add t over to it, you ended up with simply t over 2. Does everybody understand that? It's got to be the span has to be over one period for this integration to work. Take this, and it's going to be times the actual value of x of t here, and now it's times e to the minus j n omega naught t dt. It's important to note that's a minus j n omega naught, and for the actual expansion here, it's a plus j n omega naught. Follow me, class? Now that's a doubly infinite Fourier series. Now what you can do, this is right here. What I can do is take that exponential. A couple ways to do this. In terms of a sine and a cosine, does everybody agree with me that e to the j n omega naught t can be rendered as simply cosine of n omega naught t plus j sine of n omega naught t? You all agree with that? That's Euler's identity you've got to notice. Correct, class?
Yes.
So I can plug that in here, and I can say my series, x of t, therefore could be rendered in terms of a doubly infinite series as the summation from n equals minus infinity to infinity of x of t, or excuse me, of c of n. C of n times, and then instead of having the exponential, I could put, this would be c of n times the cosine of n omega naught t plus j sine of n omega naught t. I'm still doing a sum from infinity, minus infinity to infinity. That's c of n here. As such, and I could keep on simplifying it. Now, the reason I'm doing this, does everybody see I could break it up into two series where I have just c of n times cosine of n omega naught t plus j times c of n times sine of n omega naught t. Follow me? Well, in the book, he basically says that he can do a Fourier series where he's going to have a cosine and a sine instead of an exponential. I don't even bother with that. I'm just telling you right now, that's nice if you're a pure mathematician and if you're looking for some clever insight into odd or even symmetry and the value of coefficients. But we're engineers. We're applying all this theory to do analysis or synthesis. Follow me? So I don't spend any time on that. The series I work with is this. And actually, another series I'm going to show you is I'm going to take this and turn it into a singly infinite series. And instead of having an exponential, there will be a cosine. I'm going to do this not at this moment in time, but in a bit. But this gets really important because that is basically the excitations for all of the circuits at a given frequency. It's always what? Magnitude cosine of omega naught t, right, plus some phase angle. And when you do phasor analysis, you get rid of the cosine of omega naught t plus phase angle, you just put the magnitude, right, at a certain angle, and it's an assumed frequency. Correct, class? Remember that? Well, you're going to see the power in this in a bit. Anyway, that's where we were last time, and I gave you some problems to do that basically amounted to doing this integration. That was the gist of it. Follow me? How many did them? Just tell me. All right? A couple of people did them. A lot of people didn't do them. I suggest you try them to appreciate the difficulty. It's a lot of integration by parts that you'll learn to dislike, just like I did. Especially when you have to do it more than once, because it takes a lot of time. All right? So I don't like that. I like to do it a different way that the book doesn't show you, and I'm going to show you. So now, I want you to remember this. The last time didn't I do this for a square wave? I caught the value of that. Remember last class? And I said you could represent that in terms of a sinc function, basically. Y'all remember that class? I was working my way there and I just stopped. Don't worry about that right now. I'm going to show you some tricks. Now this, you take good notes on. It's not in the book, not the way I'm showing you, but it is extremely valuable. Remember, as engineers, we like to get to the answer in the simplest possible way, where the least number of mistakes can be made in the most efficient way. We're not elaborate mathematicians looking for some kind of divine insight into some crazy abstract proof. What we're trying to do is get the answer. Now, when I look at this representation, I want you to follow me on this. If I have, I'm going to just tell you one other thing too, and this is important. Remember how I said that if you had an impulse function, a delta of t, right? Matter of fact, let's make it delta of t minus some value tau. And this is going to be some functional form. This is t here. It's not going to be at 0. This would be tau. Correct, class? That's where it actually pops up. Now, if you take a look at this, this is the one thing that's so important. If I take and I integrate delta of t minus tau times any function at all, times f of t, right, dt from minus infinity to infinity. Remember, the integration is now over t. It's not over tau. What do I get out of there? You always look at where the delta function I says turns on where it goes to infinity, right? Where does that occur? When t equals tau, right? Therefore, because the integral is with respect to t, this becomes nothing more than f of tau. Does everybody follow it on that? It extracts that value, doesn't it, class? Now that I've reminded you of that, I want you to watch this, what I'm about to show you. Let's assume I have some function, and I'm going to pick a simple one, this square wave again. Square wave. Doesn't have to be a square wave, but for the purposes that where I'm going to show you the trick, I'm going to use this. And this is my x of t. And I know this x of t can be rendered as a summation, right, here of c of n, right, times e to the j n omega naught t, and n goes from minus infinity to infinity. I encourage you to keep rewriting that so you don't forget it. Make sure you just write it again. I know it gets boring. Redundancy will make it stick with you. Now that's my x of t versus time. This is the fundamental period. Do you agree with me? Remember, the purpose, the principle behind Fourier analysis is if there's any periodic function at all, I can represent that in terms of a series where the coefficient c of n times that exponential can be calculated. The coefficient c of n can be calculated. Follow me on this, class? This is the basis for what I'm doing. Any periodic function. Now I'm going to take a derivative of this. So I'm going to take a derivative of this, x prime of t. The prime indicates derivative with respect to time. How many are familiar with that notation from your mathematics courses, right? Derivative always has a little apostrophe there, right? If I take a derivative of that, let's call this height a of this square wave. All right? And I'm going to call the on time here tau. So this would be tau right there, and this would be tau plus t, and that would be just t. You get the idea. It repeats itself, right? Please watch. Now when I take a derivative of that, what do I get? If this is time. What do I get right here? Anyone? What's the derivative of this? The derivative is the slope of that, right? What's the slope of that? Infinite. It's a delta function. Do you all follow me? The delta function has a weight of a, though. So that means you're going to have a delta function right here, delta of t times a. Well, do that too well. How about if I do it like this? It's going to be A times delta of t. Follow me? Got me on that. Now what's the slope of this line from here to here? It's 0, isn't it? There is no slope. It's 0. What happens next? Now it goes down to minus A times delta of what? T minus tau. Correct, class? Keep listening. Are you with me? Give me a show of hands here. How many are with me so far? Keep going. What about the derivative at t? Huh? Another delta. That's when it starts repeating itself. Do you all see this? And it repeats itself from here on. You basically have a periodic series. Do you all agree with me? That is a periodic series, isn't it, class? Now watch. This is the important part. This is where you define this secret I'm talking about. When I look over here to this series, I can take a derivative of that with respect to time, right? And now we get my x prime of t here would now be still the doubly infinite series exists. But now when I take a derivative, I would get with respect to time, I get what? J and omega naught out in front, wouldn't I? So I would have in here J n omega naught here times C of n times e to the J n omega naught t. Now, you're going to have to just think about what I did. I simply took a derivative with respect to time of this function. Do you agree with me? You also agree that this is periodic, is it not, class? If it is periodic, it can be represented by a Fourier series, can it not? Now, this isn't a Fourier series per se. That coefficient is not a singular value of C of n, it's J n omega naught C of n. But in fact, that is a coefficient that we can work with. What we're really going to represent this is with something where it's going to be a doubly infinite series. Work with me now. But we'll call this C of n prime times e to the J n omega naught t. The C of n prime means it's related to the derivative of x of t. Now, this is the very definition of a Fourier series with the one change. I put a little apostrophe on that C of n. Correct, class? How do you calculate the value of this coefficient right here? You enact this integral, right? Well, here's a periodic series. I'm going to get this coefficient. Follow me, class? You all see I'm after C of n prime. Follow me? What do? I say C of n prime is equal to 1 over the period. The integral, I'm going to go from minus t over 2 to t over 2. And I'll make the assumption that tau is less than t over 2. So I'm just assuming that. It doesn't have to be, but it'll save me a little something when I'm doing the integration. Now I'm going to put the value of what? X prime of t in here, right? Not x of t, x prime. Follow me, class? What is x prime of t? It's those delta functions. It would be what? A times delta of t minus a times delta of t minus tau, right? Times e to the minus j n omega naught t dt. Does everybody see this is my x prime? Is it not, class? Over one period, right? It's really where? From minus t over 2. What I'm doing is going from about here up to about here. The spread is one period, but I just want to move the window so I capture this one and this one. I don't want the thing to start at a transit, where it's transferring from 0 to infinity. Follow me? So I always move my window of integration to a point I don't have to get that. Now what's this C of n prime going to be? Take a look. Well, it's 1 over the period, right? And I might as well put the a out in front. Work with me now. What goes in here? Well, this first delta function turns on at what? T equals 0. So what do I have to do? I have to extract the value of this function that's next to it at 0, correct? What is that value? It's 1, right? E to the 0 is 1. How many see this? Can you see it in the back, guys? All right, so that means I simply have a value of 1 there for this times this, correct? What about the next one? I took the a out in front. It occurs at what? T equal, say it. Tau. Therefore, I have minus e to the minus j n omega naught tau, right? Y'all agree with me? Now, what did you notice? delta functions are great to integrate by. The only thing you have to do is see where they turn on and evaluate whatever's next to them at that turning on point. Got that, class? That's it. That's why delta functions are things you look for. But that isn't the value of C of n, it's C of n prime, right? And now the relationship. What is the relationship between this and this? They're equal, aren't they? So this C of n prime is really equal to j n omega naught, right, times C of n. That came from right here. Can you all see this, class?
Yes.
Please take a careful look at this. This is the very important point I'm making. Our goal is not to get the value of C of n prime, but C of n. So now what do I do to get C of n? Very good. Simply divide by j n omega naught. And lo and behold, now we have the value of C of n without ever doing integration by parts or any kind of nasty little thing. You all see this? But what was the key? Taking derivatives until I get impulses. Follow me? That is the secret. Now I'm going to do some more of these, but I want you to appreciate what I've done. I'm going to do one other thing right here that I didn't do last time. You see this value? This is what we got last time when we did the integration. All right? That's what we actually got. What I'm going to do is go a step further. I'm going to turn that into the sinc function or into the sine stuff. So let me do that right here. Work with me now. And stay sharp here because this is so important. I use this stuff, I go through this with the radar class. We use this all the time. It saves so much blood, sweat, and tears, so to speak. Now, I had there, what? C of n for that square wave was equal to what? It was a over t, right? It was divided by j n omega naught, correct? And then there was what? 1 minus e to the minus j n omega naught tau. Wasn't there, class? Yeah. Here's a trick I want you to make sure you keep in mind. You always try to take weird-looking functions like this and turn them into something you're familiar with. Got me? Now, I've done this too many times, but I know for a fact whenever I see something like this, I'm going to factor out an e to the minus j n omega naught tau over 2, and that will give me something that's going to be easy to put in terms of a sign. Just watch this. This comes from experience. So here I'm going to say I'll leave the a over t out in front, and I'll also leave the 1 over j n omega naught out in front. And now I factor out my e to the j n, pardon me, minus j n, it's a minus there, j n omega naught tau over 2. And I'm left with, here it's e to the j n omega naught tau over 2 minus e to the minus j n omega naught tau over 2. Can you all see that, class? Just work with me here. Make sure you see it. If I multiply this times this, I get 1, don't I? You add the exponentials, correct, class? See it in the back? And when I multiply this times this, I get e to the minus j n omega naught tau, don't I? How many see this? All right, this is normal. You'll be doing this kind of stuff all the time in engineering. Now, once you have it this way, what do I know about this? What is that equal to?
Cosine.
That is what? Not cosine. If I have what? A sine of theta, that's equal to e to the j theta minus e to the minus j theta over 2j. Isn't it right, class? Y'all agree with me? How many agree with me here? Make sure you know this. So if I multiply both sides by 2j, now I have that, don't I? You all see how the theta there represents e to the what? That theta, I'm sorry, represents n omega naught tau over 2. Doesn't it, class? Give me a show of hands if you see this. So what is C of n? Well, C of n here is going to be a over t, that's that, 1 over j n omega naught here, and then I have to have that phase term, I'll put it right here, e to the minus j n omega naught tau over 2. That's just a phase. And this becomes 2j times the sine of n omega naught tau over 2. Does it not, class? Please write this down. You're attentive here. You're going to be expected to do this. All right. What might I do to simplify my life? Anybody? You can see, if you can read my writing, you can see it. That's always a stretch, though. How about those J's? Do we need them? I see a J here and a J there, right? Let's get rid of them. Now, the next thing I'm trying to do is make this look like this argument. Follow me? Are you with me? You notice I got, there's a 2 here, right? So I can multiply top and bottom by a half, can't I? And get rid of that 2. Do you agree with me, class? Multiply top and bottom by a half. It's getting close, isn't it? What am I lacking? I need a tau, don't I, class? So if I multiply top and bottom by tau, move that A a little. Now I have something where I have what? I have sine x over x, where x is n omega naught tau over 2. How many see this? What is sine x over x? Sinc. So I can say this value of c of n right here is actually equal to a times tau over t times that phase garbage. And then it's going to be just times the sinc waveform, right? Sinc of omega tau over 2. And, right? Y'all agree with me here? How many do? Right? And I better put this up. Sinc, right? Sinc of x is equal to sine of x over x. This is our definition. The alternative definition that's used at times, it's sine of pi x over pi x. Yes, sir?
What happened to the n in the sinc? It says n.
Yeah, that is my fault. Thank you for catching that. All right, thank you. It's n omega naught, actually. Right? Are you with? Yes?
Okay, so I probably missed a step, but you had the sine n omega naught t over 2, and then was that still over 2j, and then it got canceled?
Remember there's a j here, and this has 2j there, right?
On the bottom.
So j and j gets canceled, you're left with 2 up top, isn't that right? Just look here. This is 2j times the sine, isn't it? 2j sine equals that.
Oh.
Okay? If you got a question, ask it. We want people to be aware of what's going on. You can miss something subtle and it'll confuse you. Make sure you get this. You're going to see this a lot. This comes at you all the time. Now, this is very interesting and very important because I know what that sinc waveform looks like. Right? And I can see right now how this thing is basically, if I drew an envelope here, just take the magnitude of C of n. If I looked at that, I knew I would get the A times tau over T business right there, and that's where it would start, but it would have an envelope like this, right? And it would be steadily dying out. Follow me? Now, this is the envelope. The actual values would occur at what? N omega naught. So you would have 1 at omega naught, 1 at 2 omega naught, and so forth down the line if you're plotting it versus omega. But now I get an idea of how fast this actual values of C of n die off. The value of C of n squared, not C of n by itself, but the magnitude squared is proportional to the actual power at that frequency. And so this allows you to discover how the power spectrum looks in the frequency domain. This is very important on radar and everything like that. Now, if it falls off very slowly, and this one does fall off fairly slowly, then you know there will be a lot of power at frequencies not the carrier frequency, and that means it could interfere with things and such. I teach a course in electromagnetic compatibility and interference. Whenever you see sideband power being significant, you have to do something to mitigate that, or you'll be in violation of a lot of FCC laws. There's also things, well, there's with radar, well, there's reasons why you want power in a lot of other sidebands, but for the most part, you don't want power anywhere but the actual point that the signal's being, well, with a certain bandwidth, the signal's broadcast, and I won't go down that road now, but that's what you're discovering with Fourier analysis, or Fourier series analysis. Follow me? That value of C of n tells you really the square value of that tells you where the power spectral density is in the frequency domain. Now, we do another problem. I'm going to make it a little more complex. You see, the idea here is you're going to keep taking derivatives until what? You get impulses, right? Everybody see that? We're going to do the next one. It's going to be this one. Write this down. It's going to be a little different. This one, I'm going to have the waveform go up to a value of A at the point tau, and then stay there until I hit the value of t over 2, and then it's going to go to 0, and then at t it repeats itself. So it looks like this. You get the idea, follow me? And this is now my x of t. Now this is a good one to remember. So that there is the period t. Do y'all see me now? See this?
Is that tau and then t over 2?
This is t, capital T over 2. This is tau. How about if I make it a? That way we won't have a problem. Are you okay with that?
Yeah.
I'm sorry if I'm not trying to confuse you. They use tau all the time. By the way, for that last example over here, there's something I didn't point out to you, but I want to. The ratio of tau over t is really what in terms that you know? You've had this. Duty cycle, isn't it? Or duty time? Y'all know that? It's the percentage of the pulse that's actually, where the signal is going to be on in a clock pulse. Most of the time it's 50% for clocking, standard clocking. But in radar work, it can be 10.1, it can be 0.01, and it depends on what it's actually used for. All right, now for this one, let me just point this out. X of t, right, is represented by a Fourier series. The summation from n equals minus infinity to infinity of c of n e to the j n omega naught t, right? Now keep watching. This is a good one. We're going to take a derivative of this. Follow me? First derivative does what? This is t here. What happens, guys?
Square the impulse.
Well, what happens between 0 and a? It's going to have what? It's going to have a slope of a over small a, right? This is going to be x prime of t. Do you all agree with that? And it stays there until I hit a, right? How many see that? Right? It's just the slope of the line. You all see this? This is very obvious, but you must see it. Now what happens?
Goes to 0.
Now it goes down to 0, and it stays 0 until,
T over 2.
right, and at t over 2, that would be a, this would be t over 2, what happens?
Negative a impulse.
Right, very important. Negative minus a times delta of t minus t over 2, capital T over 2, correct?
Yeah.
Now keep working with me. I've got a square well here, and then an impulse. And do you all agree it's going to repeat itself? You're going to get that same pattern again, right? And then, so that's a periodic function. Do we agree with that?
Yeah.
Right, this would be again minus a times delta of what? It would be t minus t over 2 minus t, right? Now it's skewed that way, and this would turn on at t, and it would shut off at t plus a, and we have a height a. Do you agree? Now keep watching. What would you do now? Remember,
Take a derivative.
I'm after just something that has impulses in the series. Obviously, partially true here, right? I got half of it with impulses, right? So now I can do something. I can say that this function x prime of t is represented by two functions. It's represented by one that is just the square wave, plus one that is just the impulse. Are you with me? How many see this? So what I do is say this square wave function here will be called x1 prime of t. Are you with me? Remember, it's a derivative of the first one. So in fact, this x of t is actually made up of x1 of t plus x2 of t. Are you with me? Now, that's x1 of t. This, in all its repetitive stuff, is going to be my x2 prime of t. Do you agree with me, class? Think about what I've done there. Now, x2 prime of t is just the way I like it. impulses, right? How many agree I can get C2 prime, right? Cn2, right? I can get that value and I'm going to get it. So now I can say this x2 of t here, right, will be represented by a series where n goes from minus infinity to infinity. I'll now call it Cn2. There's a bomb. I hate this thing does this to me. Hey, why don't you come up here and try to kill it? Right? And then it's times e to the jn omega naught t. Correct, class? Just put it, that's a 2 there with a prime. You all follow me here? I took one derivative to get that from the x2. Correct, class? Now, what is this value going to be of Cn2 prime? Well, Cn2 prime would be 1 over the period, right? Times the integral of x2 of prime of t over a period. What is x2 prime of t? It's that delta function. Do you all see this, class? Please do. And that delta function is what? Minus a times delta of t minus cap t over 2, right? Has to go from minus t over 2. Let's go from, tell you what, on this one we're going to go from 0 to t. Has to be over a range of t. Doesn't it, class, the integration? So I'm going to slide my integral. I'm not going to start at minus t over to t over 2. I'm going to go from 0 to t, right there, for this one. And then it's going to be times e to the minus jn omega naught t dt. Are you with me? Please work with me. What does that give me for the value of Cn2 prime? Well, it's going to be what? Minus a over cap t for sure. That's a scaling factor, correct? It's just a coefficient. What about what this does? What happens when I do the integration of the delta function, class? Where does the delta turn on at? T equal. And I have to evaluate this when t is t over 2, correct? Please watch this. So I simply multiply this as e to the minus jn omega naught, right? T over 2. Now, remember, that's Cn2 prime. It's not Cn2. And frankly, I didn't write this, but each one of these has a Fourier series, doesn't it, class, representing it? It's just like the first, just work with me here. If I wanted to get Cn2, what would I do? One derivative, divide by jn omega naught, 1 to the first power, right? So when I divide this by jn omega naught, or this by jn omega naught, now I have Cn2 that is associated with the Fourier series for x2. I don't care what x2 looks like. I got the derivative of it. Correct, class? Now keep working with me. Now, here, I don't have an impulse function yet, right? That's x1 prime. What do I need to do to get one? Another derivative, right? Now we come down here, and I'm going to have to, I'm not good at this, but we're going to just work with me on this one. So now I focus only on this and this, right? When I take a derivative, please watch this, class. This is so important. When I take a derivative of this, this is going to be my x1 double prime of t, correct? What does it look like? Right here. Scale factor in front of it. It is a over small a, right? So make sure you put that in there. So it's a over small a delta of t. You don't have to write the delta of t. I'm doing it to make sure in your mind you realize it's an impulse. What else? Keep going. At small a, right? At small a, now it comes down to minus a over small a, delta of t minus a. Correct, class? You got that, everyone? What am I going to do next? I know a lot of people see it. I'm going to get C of n1 double prime, not single prime. So now, let me do it over here. You'll thank me for this. Believe me, you're going to thank me. when you get into some of your other courses, they're gonna ask you to do Fourier series analysis for coefficients. And you aren't gonna have to do the darndest integrals, thank God, for most functions. Now, obviously, this assumes that if you continually take derivatives, you will be able to get impulses. But that's most of your waveforms. It can be approximated as things like that. Think about it. Just think of the standard waveforms that you have. Rise time, hold, fall time, right? Those, they usually are approximated as straight lines, almost always. All right, so now I'm gonna get my Cn1 double prime. 1 over the period, right? Here, this one I'm gonna integrate. I'm gonna go from, remember I have to integrate over a period. I'm gonna slide this one down from minus t over 2 to t over 2 so I can capture just these two. And I don't start at where one's transition. Do you follow my logic on this? Remember, you can integrate over any period. So wherever you start, you have to go down a period and stop. So I always say, take your window. When I say integrate, it's the range for this integral where you're calculating C of n. Always move the window so that you don't have a transition happening where you start or stop. That's the idea. Start below, stop above. And remember, it's only over a period, not an infinite. You're not integrating over some infinite range. So for this one, I'm going to go from minus t over 2 to t over 2, and that should capture everything. And what is this going to be? It's a over small a, delta of t minus delta of t minus a, right? Times e to the minus j n omega naught t dt. Do you agree with me there? And that defines the value of the double prime C of n, right? C of n double prime, really Cn1 double prime. It's associated with two derivatives. What's this going to be, guys? Well, it's going to have a over t times small a, right? And then keep going. This turns on at t equals 0, e to the 0 is 1, thank you. Minus, this turns on at a minus e to the minus j n omega naught a, right? How many see this? That's C of n 1 double prime associated with an infinite series for x1, right? What do I need to do to get just C of n1?
Divided by j and omega squared.
I took two derivatives, I have to divide it by j n omega naught squared, right? And you're right about that. So this is divided by j n omega naught squared. Now, I could talk to you and say, how many see I could probably turn that to a sign up top? How many realize that? By pulling out the e to the minus j n omega naught a over 2. And yeah, you can work that way. And I could probably get a sink out of there, but I'm still going to have an n omega naught downstairs. Trust me, you're not going to get rid of it all. There still is going to be that. I'm going to leave this one, this right here now becomes C of n, right there, C of n1. Now we've got C of n2 over there and C of n1 here, right? Now watch. We're going to put them all together and get a single series that represents that spike or that waveform right here, where it goes up, stays, and down. Now we can say that now the value of x of t up there is going to be equal to a series. It's going to be a doubly infinite series. And here you're going to have two coefficients. First, you can start with this one, so I have a over t small a times 1 minus e to the minus j n omega naught a divided by j n omega naught squared. That's the first one. Plus the second term, which is, that's minus a, isn't it?
Yes.
Yeah. So it's minus a over t times e to the minus j n omega naught t over 2. Right? That's the coefficient. That's C1, C2, all times e to the j n omega naught t. And that, in fact, represents the value of x of t. Now, I'm going to show you a couple other things shortly. But I want to tell you one thing about this. This is so important. that you can take this, and we're gonna do this in MATLAB. How many have worked with MATLAB? All right, I'm gonna give you a piece of advice. Don't hate MATLAB. Don't despise that, don't hate Python, and I'll tell you why. Because your job, my wife right now is working for a company, she's worked for Intel for years, she's working for another company in the area. Their prototypes are done in MATLAB, or Python, or both. The prototype is the first program you write before you implement it and turn it into a C code or something like that in a compiled code that's used over and over. The reason you write it in these codes like Python or MATLAB is because they're easy to do relative to writing in just C++ or whatever, Fortran 90 or whatever you've learned. It's much easier to write in a higher level language. Now the thing about MATLAB people hate is there's a learning curve. But thank God for YouTube and Google, because if there's something you want to do in MATLAB, just get on YouTube and type it and you'll find out how to do it. If there's one thing people are good about is when they figure something out, they want to get recognized for it. So they stick all this information up on YouTube. And you can, if you just Google it, you'll find documents, but I prefer to get on YouTube because that's where actually the students talk about it normally, not like professors that try to hide the truth. So, y'all see that right there? We're going to prove a lot of this stuff. We're going to actually do this in MATLAB and show you how that darn thing right there will exactly show you this in the limit as you get a lot of terms, a lot of terms. Yes, sir?
What happens to the denominator on C into the final?
Oh, I forgot the J and omega naught. Sorry. Thank you. Thank you very much. I somehow forgot that. I apologize. Thank you very much. But yes.
So that solution ends up being purely real. It's not like a complex.
When you do the sum, you know, you can't sum from minus infinity to plus infinity. You give me that one?
Yeah.
All right, so you get a limited number of terms, say minus 50 to plus 50. All right? Now, one other thing I'm going to tell you about this, you never sum where n equals 0. That one is the DC term. You have to add plus C0 out here by itself. So what you want to say is n unequal to 0 for that part. All right? You never do that because think about it, you get 1 over 0, right? You technically would have to use L'Hopital's rule to actually calculate that. So you always put C0 out by itself. That's just the average value of the function, the DC value. You follow me in that class? C0 is just the average value of the function. What is C0 if you just look at the definition here? Well, it was, I didn't put it here, but in general, C of n is equal to 1 over the period, the integral from 0 to t or over any period, x of t times e to the minus j n omega naught t dt. Well, when n equals 0, you're just integrating x of t dt and taking 1 over t, correct? That's the average value, or DC value. That's all it is. Understand, class? All right, now this stuff is so important. The next thing I'm going to do, I'm going to give you some homework problems like this and give you the answers. I want you to work through them, because this is what's going to happen on your quiz this Friday. You're going to get this stuff. But what I'm showing you here is so vitally important. Now I'm going to do something with this series. I got 10 minutes left, roughly. I mean, first, are there any problems that you wanted me to work that I gave you? Now we can beat these problems out in a second, most of them. I gave you several, didn't I? All right, let me just show you one. Let's just do this together using the method I've showed you, the new improved way of doing things instead of all these integration by parts and newfound ways to cause anguish. All right, ready? Listen, do you have one for me, or should I know one I'm thinking about, but, or not?
Do the one you're thinking about.
All right, follow me. This is like something that you would angst about, but if you do it the way you were just shown here, it's a breeze, it's simple. All right, ready? Here's the function. This is x of t. 5/4 t, and then 3/2 t, and so forth. It repeats itself. The period is t, right? I could assign values, but forget it. The height is a. All right, now, look, y'all know, if you were to do this the normal way, you would have to integrate this function from here to here times e to the j minus j n omega naught t dt to get the first, right? Then you have to integrate a second function here, which is the line, another straight line with an offset, and it would be another function that has the form of t, right? Plus a constant times the scale factor, and integrate e to the minus j n omega naught t dt, and it's two integrations by parts and a lot of angst. We ain't gonna do it that way. We know that this is equal to the summation of c of n e to the j n omega naught t from n equals minus infinity to infinity. Tell me what to do, guys. You've got all the information you need for me to do this. What do I do next?
Take the derivative.
Let's take a derivative once first. All right, what does one derivative do for me?
Get our constant values.
What do I get? Start at 0, how high does it go?
Yeah.
Thank you. You're right, 4a over t, correct? Make sure you get that. Got to get that scale factor. And it stays there until what?
T over 4.
And then what happens? You're right.
And then it drops.
Minus 4 times a over t, correct? Do you agree with me?
Yes.
And what happens at t over 2?
Goes to 0.
It's 0. And then it repeats itself. Do you agree with me, everyone? I'm just showing you it repeats, correct? That was one derivative. Yo, are you with me? I mean, you agree with me, right? What do I do next? That was one. Another derivative, right? Now, make sure the scale is right. This is where people mess this one up. All right? What am I going to get? I'm going to get an impulse, correct? Right? What's the weight in front of the first impulse?
4a.
And it occurs at 0. So now I get a first impulse here that has a weight of 4a over t, and it's at 0, right? Keep going. The next impulse is at
T over 4.
t over 4, and the weight on it?
Negative 8a.
Thank you. Twice that, minus 8a over t, correct? Right? People mess that scale up all the time. I'm just saying that.
Why is it twice?
Huh?
Why is this?
8, because you went from 4a over t to minus 4a over t. The scale has got to be proportional to the rate, the change, right? So that's minus 8a over t, right? Keep going. 0 here, guys, until,
T over 2.
and what happens at t over 2? Back up, how high? 4a over t, right? Now, y'all agree we can get the coefficient associated with that, but it's a double prime coefficient, right? I'm going to do it over here. I can say now my Cn double prime is equal to 1 over the period times the integral. Listen, I'm going to go from about here to about here over a period. I'm going to capture all of them, all right? So I'm going to start at like minus t over, I don't know, t over 10 to t times 9 over 9/10 t. Basically, I'm just moving that scale so I capture them and I don't worry about it. I take a look at the first coefficient. I've got 4a over t out in front. I'm going to leave it there. Then I have delta of t. Then I have minus 2 times delta of t minus t over 4, right? And then I have plus delta of t minus t over 2. Correct, class? All times e to the minus j n omega naught t dt. Do we agree that that is in fact c of n? Yes, sir?
So you can't integrate from 0 to t and still have that first.
Well, the
impulse.
problem with this is, what do you do right there? It's 0. The impulse is just going, it's going through its transition. Never start an integration where a transition occurs. Because the logical question is, well, do half the value? What do I do? Because I'm starting at something that's just beginning to have a change, right? So don't worry about it. Never do that. Always move the sliding window to a point where you don't have a transition.
Good.
Now, what is this value going to be? Come on. Y'all agree that the 1 over t can come out in front and the 4a over t can come out in front. Y'all agree with that? So I'm going to have 4a over t squared. Right? Now keep going. What next? This occurs at t equal, so I got a 1, right? Then I have minus 2, this occurs at, so I'm going to have e to the minus j n omega naught t over 4. Then
Plus e to the
e to the minus j n omega naught t over 2. Correct, class?
Yes.
All right, that's c of n double prime. What do I need to do with that to get c of n prime, just by itself? How many? J n omega? J n omega squared. Right. I think you guys got it. I'm proud of you. J n omega naught squared. By the way, what is j squared, anyone? Negative 1. So you can throw a negative 1 in there if you don't like that one. Tell you another trick with this one. I'm not going to beat you up on this one. But I can see right here, you'll be able to factor something out of here so you can in fact get a sine, or, well, in this case, you're going to be able to get, I think this thing right here is a perfect square, all right, of something, but you could turn it into a sine. Don't worry about that right now. I'm basically I'm running on fumes here as far as class time. But y'all see how you got that. Now, it beats the daylights out of doing integration by parts a couple of times, especially when you get wacko ones. I mean, when you get this, and then something like that. Because those drive me nuts when I was in school. You spend hours doing these crazy integrations that the professor just loves to think about you doing because you suffer the way you should. The object isn't to suffer, it's to learn how to solve problems. All right, if you got questions, see me. Remember, Quiz Friday on this stuff. For you serious. And Friday I'm going to show you the next tricks, which is really going to move into